Hello and welcome. In this video I'll be covering section 8.1, which covers the concept of the law of sines. My goal for you by the end of the video is to be able to use the law of sines to solve some of these oblique triangles, as well as to be able to find areas of triangles given either two sides and an angle or potentially all three sides. So thus far in class we've only been able to solve triangles that we knew were right triangles. So this specific law will allow us to transition into some of these triangles that are not a right triangle. So collectively we'll just call those oblique triangles. And again, still same general thing. If it says, or if a question asks you to solve a triangle, that basically just means I need to be able to identify all three sides and all three angles as far as their measurements are concerned. Each of these problems should be providing you with at least 3 bits of info, so it's entirely possible that you may have to find the other 3 that are still missing. So as far as any time you're given at least one side and any 2 other measurements, we should be able to solve the triangle no matter what, even if it's a right or an oblique. If it happens to be a right, then I can fall back to SOHCAHTOA and Pythagorean theorem. Or if it's oblique, we can utilize this function, or sorry, not really function, but this law of sines, and then eventually we'll learn a third strategy called law of cosines in the next video. Alright, let's go ahead and talk about some of the situations that are going to be provided to you as far as the given info in a problem. The 3 that you can currently see on the screen are going to be ones that are associated with a law of sines approach. Notice again, these are not right triangles, so Pythagorean theorem and SOHCAHTOA will not be options, but we can utilize law of sines, which will be something I discuss here in a moment. But again, you might recognize these kind of 3-letter groupings back from like maybe an earlier class where you had to do like proofs of triangles. We're not doing proofs, but I just wanted to at least mention like what each one of these is. The first 2 that you see, notice you're given 2 angles and a side. It's just a matter of is it the included side or the non-included side. One of the non-included side situations would be the AAS, which you can see an example of there, where it would be the 2 angles and then the side that's actually across from one of the angles. You may also have an ASA, which is the 2 angles where now you do know the included side, so it would be the actual side that connects the 2 angles. Or there's the third situation, which, if you recall, didn't work with proofs, but it is something that still can allow us to draw a triangle. It's just potentially I might actually have multiple solutions or maybe no solutions at all. So that's going to be one that we'll probably spend the most time in this video on, is the side-side angle situation. We're going to have 2 consecutive sides and then the angle that's not included, so it must be across from one of the sides that was provided. This particular one is what's called the ambiguous case in most math textbooks, but again, that'll be something we discuss a little bit later. We'll kind of go through and see what one of the 2 solution situation is, what one of the 1 solution, as well as the why maybe I wouldn't be able to even draw a triangle at all. The other 2 ways that problems can be presented is going to be more of a law of cosines, which is not a part of this video. It'll be a part of the next one, but those just to, while we're talking about what could be given to us, we have also the ability for side angle side, so the 2 sides with the angle that is included, as well as the side. Let's say I gave you all 3 sides, I should be able to actually solve that triangle as well. Again, these 2 are more going to be what the next video will discuss. So kind of put a pin in this stuff, but again, just wanted to, while we're talking about it, at least present, here's the 5 main ways that they can present these problems that are solving an oblique triangle. Alright, so now actually on to what the law of sines actually happens to be. So law of sines, as you can see here, is if I have some triangle, ABC, again with normal lettering, so side A and angle A are across from each other, side B and angle B are across from each other, side C and angle C are across from each other. So again, normal naming. They don't have to be named triangle ABC, but just as a general template, notice we have 3 different proportions that must remain true for law of sines. So basically it's whatever the side is proportional with its sine of the angle, in the same way for each pairing. So you can go with either of these versions, where either you put the sines on top or you put the sines on bottom. So it's just a matter of being consistent. I personally prefer the second option over the first option, but again, as long as you're consistent from start to finish, you can technically use either one of these versions for it. So ultimately, how we would start these types of problems for law of sines is we try and find out of those three ratios which one I actually know both variables for. So in other words, which one I know either both A's, or maybe I need to know both B's, or maybe I already know both C's. But once I have one of those ratios where I don't have any variables left anymore, that'll be something I use and then set up a proportion with one of the other two and individually solve for either the A's, the B's, or the C's, depending on what I've been provided. As far as when will I use law of sines, it's going to be, as mentioned earlier, one of those three cases where either I've given you two angles and a side, or potentially the one where I have two sides and the non-included angle. Again, that SSA situation is the one that's going to be the ambiguous case. This is going to be the either no solution, one solution, or two solutions. The other ones, if I ever know two angles, there's only one third angle that can possibly add up to 180. So those are usually the easier, at least as far as the law of sines type of problems to present, because there's always just one guaranteed solution. It's the side-side angle, the ambiguous case, if you will, where that's where we'll have to look a little bit more in depth and kind of have a little bit more specific approach to solving that problem. All right, so let's go ahead and jump into our first example here, just to kind of see how the setup for law of sines works, as well as just maybe how we can go through and actually do some of the solving. So I will be popping back and forth between the calculator and the screen, so you feel free to follow along. Just remember, with any calculator that you're using, especially with this specific section, we need to make sure that the mode of our calculator is in degrees, because after all, as you can see with this problem was given, I was given three things here, and the two angles have a degree marking on it, so that is the unit of measure. So again, just making sure that our calculator is set up in the right way. So for this one, notice we actually have a pair of E's, so that means I should be able to go straight to setting up our expression here. Actually, let's just go ahead and get a picture so we can kind of see what's going on here. Let's draw the visual. So for this one, it looks like I have a E, a G, and I feel like we can pick whatever letter we want, but F seems like a logical letter to choose for the last one. So I'm going to go ahead and go with the two angles that I have so far. Let's call this bottom left one my E. That one's 43 degrees. Across from E is side E, which is 4.56. And then I'm going to go with just the bottom right one here is going to be my G angle. So that's my 57 degree angle, which means across from that would be side G. And like I said, we can pick whatever letter we want, but F makes the most sense to me, even though it didn't tell us the name of this one. So that means the side across from it would be side F. So as far as what do I need to identify, it looks like I need to know what angle F is, I need to know what side F is, and I need to know what side G is. Those are my three unknowns that I need to figure out before I can move on to the other problem. If I can find those three, combined with the original three, that would give me all 6 parts that I would need to be able to actually quote-unquote solve the triangle. So when it comes to our setup here, let's go ahead and start making those ratios. The first one I would go with is the one that I have both letters with. Sine of E, which would be sine of 43 degrees over the side E, 4.56, is going to be equal to the sine of G, which we know that angle is 57 degrees, over side G, and then also should be equal to sine of F over side F. Now ultimately right now I have 2 out of the 3 angles, so I should be able to, forgot to put a little degree marking on that, but anyway, go ahead and find that third angle. The easiest way to do that would just be for this angle F, just do 180 minus those 2 angles together, minus 43 minus 57. And since 43 and 57 added together is 100, really this is just 180 take away 100, which is 80 degrees. So really what I can do now is, instead of having that capital F down here, I can actually switch that to its value, 80 degrees. And now I should be able to pick any pair of those. I'm going to go ahead and pick these 2 to start, and then after that I'll take the original one and that one and basically set up those 2 proportions and solve. So if I go ahead and do that off to the side here, I'd have sine of 43 over the 4.56 should equal the sine of 57 over G. And now it's just solving a proportion, which hopefully we've learned in a prior class. But the basic shortcut we can go with here, I'll try and mimic. If I ever want to solve for this G, ultimately I'll just take the 2 that are across from each other and multiply those 2 together, and then divide by whatever is left over. So for this specific example, my G is going to equal the two things that are across from each other, so the 4.56 times sine of 57. And then I'll divide by whatever I haven't used yet, which in this case is this sine of 43, so I'll have sine of 43 in the denominator. And now it's just a calculator exercise. So if I go ahead and bring up a calculator here, trying to remember those numbers, I've got the 4.56 times sine of the angle. I'm going to bounce back 57, the other angle is 43, so 57 degrees was on top. Close the parenthesis before I press divide, but then now divide by the sine of 43. Close that parenthesis. Again, double check that our mode is in degrees, which this happens to already be, as you can see at the top of the screen. Press enter, and it gives me that this side length is approximately 5.61. So if I go ahead and switch back, this is 5.61, and I'll go ahead and put that answer on the blank. So notice now I've got one blank left. Oops, I put that on the F, not the G. 5.61, there we go, that's a little bit more appropriate. And then now we're going to do pretty much the same thing, just using the other ratio for F. So if I go ahead and do that maybe over here in the white space on the right here, the open space that I have, it'd be that sine of 43 over 4.56 that I'm going to use again. Again, when it's possible, I would say always use any information given things that you found, because in case you made a mistake with something you found, you would be guaranteed to pretty much have your next answer be wrong. So instead of using the G ratio with that 5.61 that we just found, go back to the original. Since I know 43 and 4.56 are 100% accurate because they were provided for me, that still can make it to where I could still successfully solve for F in case I did make a mistake when solving for G. Now if you were accurate with G, then it technically wouldn't matter, but again, it's just kind of a little safer if you can use the original info. Just like before, I'm going to do the same cross product and then divide. So for this one, my side F would equal the 4.56 times sine of the 80 degree angle, and then divided by the sine of 43. And let's go ahead and pop over to the calculator. Really, we could just trace the previous answer, and the only thing that's really different is instead of the 57, I'm just going to switch that 57 to an 80, just type right over the top of it, and press enter, and that gets me my last side of 6.58-ish. 6.58. So now at this point we can always do the same general thing that we should do with any solution, is just double check that the logic follows. Across from the biggest angle should be the biggest side. So out of my sides I had a 4.5, I had a 5.6 and a 6.6 almost. The 6.6 is across from the 80 degree angle, which is the largest, so at least that one checks that box. Across from the smallest angle, 43 degrees, was the smallest side, and across from the middle angle was the middle side. So as far as the logic is concerned, all of the numbers at least make sense. There's no big red flags with this. But at the same point, we don't necessarily guarantee they're correct. It's just a matter of if it's following logic, there's a very, very high likelihood that we've done things correctly. Go ahead and move on to a second example of this. This specific one, again, notice now this time instead of it being an angle, and a side, now I'm saying I have an angle, side, angle. So what we could do is just look at what type of angles we got. We've got angle C, we've got angle B, and then we also have side A. So it seems like this one has to be named ABC. I have one obtuse angle, so I'm going to go ahead and just at least try and draw an angle that is obtuse on there and know that that's going to be my C angle. So that's 110 degrees. And then I can pick wherever I want to put the B. I'm going to go ahead and just go with B up here in the top left, make that 43 degrees, which then means this last one must be angle A, and we do know that across from angle A was side A, so we know we can put 13 on that side. So just like the last problem, we should have the ability to solve for that third angle just by doing 180 minus those two added together, so it'd be minus 110 minus 43 in sequence. Or I could do 110 plus 43 and get 153, subtract that from 180, and regardless I should get that there's 27 degrees left over. So adding that to my picture, now notice I've got at least one ratio from law of sines where I know both values. I now know both A's, so it'd be the sine of the A angle I know over the side A that I also was provided. And now I should be able to use that to solve for either the side C or the side B, which are the other two unknowns. So I'm going to go ahead and just go alphabetical. I'm going to go after that side B first. So this would be sine of the angle B, 43, over the side B. And just like we had done before, cross multiply the two that don't have any variables. So that would be the 13 and the sine of 43. And then divide by the extra ratio I haven't used, or extra part of the ratio that I haven't used, which is the sine of 27. So altogether my B value is going to equal that product of 13 with sine of 43 divided by the sine of 27. And just like before, just bring in a calculator. I've got 13 sine of, I need to remember those numbers, 43 on top, and then divided by sine of 27 on the bottom. Press enter and it gives us a value of about 19.53. So B in this case equals approximately 19.53. So if we wanted to keep all of our answers somewhat close to each other, maybe go ahead and write that up here, and we'll end up boxing all of this together in the end. So now if I go ahead and do a similar step, but to solve for side C, I'm going to go ahead and use that same ratio of sine of 27 over 13 as like my key. And this time it's, instead of being the angle 43 degrees, now I'm going to reference the angle 110, because that's the C angle, and that should let me solve for the side C. So just like before, cross multiply and divide. My C value for this one would be the 13 times sine of 110 all over sine of 27. And let's see what that turns into when I bring in the calculator. So just like before, I can probably reuse whatever I just typed in, because the only thing that's going to change is the 43. What gets a little tricky with the calculator input here is if I type in 3 digits, it's going to replace all 3 things, including the parenthesis at the end. So what we can do is just do an insert, so that's second of delete. And notice now it's blinking clear. Now if I type in my angle 110, it pushes the numbers down, and I can just physically delete the 43 now, and everything is all good without me having to retype everything after the sine of 110. Anyway, if I go ahead and press enter, that gets me this 26.91 approximately. So 26.91. And if we do a quick little glance here, did the bigger side have the bigger angle across from it? Well, the biggest side I see, I've got 13, 19, and 26. So across from the 26, that is the biggest angle, right? 26.91 would be there. And then across from the B, well, side B, 19.53 that we found, that was the middle angle. So as far as logic is concerned, again, the sides and angles at least are matching up. Across from the smallest was the small side. Across from the biggest was the biggest side. So again, everything kind of checks out with what we got going on here. All right, so now we'll go ahead and jump into that ambiguous case mentioned earlier. That's the, maybe I won't have a solution, maybe I'll just have a single solution, maybe I'll have 2 solutions. Hopefully these visuals that you can kind of see on the screen right now will help with the how should I know whether I have 1, 2, or no solutions. Each of these cases, if it helps, you can always think of like, what would the height really be? So notice if I use this first picture on the far left, if I just drew that dotted line and said, okay, that's my height. If I ever need to find the height of any of these, for this example, it would just be whatever the adjacent side is. So as you can see with the picture here, my adjacent side for the angle would be this C, and then the actual angle itself is right here. If I look at how that's related to the H, that would be a sine ratio. So I'd have, technically, if we wanted to write that, it would be, let's just write it underneath here, I'd have sine of B would equal the C value over the H value, the H value over the C value, which then to solve for H, I would just multiply by that C. So really kind of the general shortcut for each of these. If I ever need to have what is the height of this, I'm going to go ahead and just put it centered on the screen here. So hold with me here. I've got the height will always equal the C value, or the side that was provided that was a different letter. So notice again with the given info, it gives me angle B, it gives me side B, so those two are the ones that match. Then I've got this different letter. In this case, we're saying it's the letter C. Utilizing that to go through and identify each of these parts, I'd have H equaling the C times sine of B every single time, again making sure that I have my calculator in a degree mode. So if I could find, for this first situation, right, basically we look at all of the cases of if I have an acute angle here, if the height actually is the exact same as the side that they provided to me that was across from the angle, so in this case if the height matched B perfectly, that gets me the one solution and actually creates a right triangle. So notice with this one it was a right triangle here. If the B value is actually equal to that height, then that just makes that 90-degree angle there. So I could fall back to SOHCAHTOA and Pythagorean theorem if I really wanted to, but technically law of sine still would work as well. Now if that side across from the angle in this first case is actually not even bigger than the height, then at that point it would never be long enough to actually close off a triangle, hence why it would be a no solution situation for that. The probably trickiest part of this is, what about when would there be two solutions? So that would basically be if the B value was large enough to overcome that height. So in other words, if the height was actually a smaller value than the B, I actually have two different ways I could potentially go if the B value was actually less than the C value. So that's where, again, take note with this, if the B is actually less than C, or the side across from the angle is less than the side that's next to the angle, that's basically one of these two cases where, or actually one of these three cases where it's either going to be no solution, one solution if it's exactly the same as the height, or it will be two solutions if it happens to be larger than the height but less than the B, or sorry, less than the C. So in that situation, you can kind of think of it as I would have this kind of isosceles triangle that would happen here, because the B value is obviously going to be the same number for both of these cases, and that kind of makes this first angle C actually match this other angle over here on the left, C. But I would actually want to know what the angle inside is. So this angle that's inside, the kind of key to that problem is this one would be like my second C if the angle here was named C. And notice that would be basically 180 minus that first C, because after all, this situation right here that you can see, those create a line. And if I know the first angle is that acute angle that would match this one that's also marked in blue, to get the angle I just marked in red, that would have to be its supplement, or it would have to add up to 180 with that specific thing. So that's kind of the key to that problem, which we'll work through an example of that. But that second solution is always going to be whatever the angle is that you find first, subtract it from 180, that'll get you the same lettered angle in my second solution, that now I would have 2 out of the 3 angles, so I should be able to solve everything the same as like the last 2 examples. Now, one thing that is kind of nice is if the B value and the C value are the two sides that they give you, if they're either the same or the one that's across the shape, so in this case the side B is the one that's across from angle B, if that one's ever the same or larger, that will, no ifs, ands, or buts, always just be a single solution for that situation. So that's usually a good start, is just identify, is the side across from the angle bigger than the other side provided? If it is, you know it's 100% just a one solution, and you'll solve everything the same like as we did the last 2 examples. Again, utilizing law of sines, because this is, again, an SSA, which, as mentioned earlier, does require law of sines to be able to actually go through and solve. Now, all 5 cases mentioned on the previous slide, notice the angle was given to be an acute angle. What's actually a lot easier is if I have an obtuse angle. If we kind of think about the 3 situations, if I have, again, the same angle and sides provided, if I have the side across from the angle being larger than C, then it's going to be basically a one solution, and if it's either equal to or not bigger, in other words, if the side across the shape is smaller or actually is equal, then at that point I wouldn't have the longest side across from the obtuse angle, so it would be these 2 first cases where there just wouldn't be a solution. So obtuse angled triangles, or obtuse triangles, if I just wanted to use a simple name, basically it's the side across from the obtuse angle has to, no ifs, ands, or buts, be larger. So if you look at the side that's across from the angle and you notice that it's already smaller than the other side they gave you, you can with 100% certainty go, yeah, there's no solution, and just go ahead and move on. What is nice with at least the calculator, as far as that's concerned, if you tried to come up with a solution but it didn't have one, your calculator is going to just continually give you error on your screen. So that's also a good red flag of, in case you forgot to look into, like, is this the one none or two solution situation. If it's the no solution, your calculator just won't even give you a solution. So at least that part is kind of nice as far as like if you accidentally forgot to look at it, your calculator still will kind of nudge you in the right direction in that event. The two solution one is the easiest one to potentially forget, but as you can see here with an obtuse angle being provided, really it kind of narrows itself down to there's either one solution or there's no solution at all. So this usually is the one students prefer, is having an obtuse angle, because it does make things a little bit easier to, I guess, solve, because it's either going to give us an answer or we won't get one, and then we can kind of move on to the next question afterwards. So anyway, from here on, I'm just going to work through a few examples of this, and then we'll transition to some of the area formulas here after a bit as well. All right, as mentioned, we'll do our first example here. Let's go ahead and jump into at least drawing a picture. I do have an acute angle, so this is going to be a 29-degree angle I'm going to put down here on the bottom. And I'm going to say that the side across initially maybe is not going to be long enough. And then the side next to it, or the different letter, notice in this case is the side 20, or a length of 20, so I just put that in between. So that kind of tells me that if there is an angle down here in the bottom right, it's going to be angle C. And we'll go ahead and just maybe approach this and go, let's find out how far this gap is and see if 15 is even big enough to overcome that. So again, the shortcut here for the height was, as mentioned before, it's just the adjacent side to that. So in this case, it would be the 20 times sine of the angle each time I ever need that height. So if I go ahead and bring the calculator in, 20 sine of 29 is what I'll be typing in. I'll go ahead and clear all that stuff out. 20 sine of 29. And notice that our height comes back approximately 9.7, but regardless, a number of 15, right? That was 9.7 approximately. 15 is definitely large enough to overcome that gap if the minimum distance there was 9.7. But it also rules out the one solution situation, because the only time that the side across, if it's less than the side that's next to the angle, the only time it would be a one solution is if it matched the height perfectly. For sure 15 is greater than that, right? That is definitely a number less than 15. So that tells me that this is going to be the two solution situation, because that side could come down to the right as I have there, or it potentially could come down to the left and still would create that same thing. So if I maybe draw those two triangles off to the side here, I've got one triangle would look something like that, and then the other triangle would look something like that. Or again, I would know the 29-degree angle that goes in the bottom left. I would know the 20 side length that goes here on the top left as well. And then I've got the side length of 15 that would be on the other side. So regardless, I'd end up with a C1 and a C2 situation, which then tells us our last angle, A1 and A2. Notice they're also going to be two different things. And then I've got two different sides for A. So I've got two total solutions, 6 complete unknowns, 3 for each. So let's just go ahead and start tackling our first solution. So I'm going to go ahead and just try to set this up. We need to figure out what the, let's see, they gave us C first. So I'm going to find C1, which then means once I get that, I'll end up, because of, as we mentioned earlier, this angle here is going to match this angle here because of the isosceles triangle that's kind of getting cut off. My C2 is just going to for sure be 180 minus whatever the first C1 that I solved for. So if I go ahead and get the ball rolling as far as setup is concerned, I can go ahead and use the ratio that I know both of, which are the two B's. So it'd be sine of 29 over the side B, which was 15. And then I'm kind of forced to solve for the C because I don't know either of the A's. So I know for sure I can go ahead and set that up. But this is, again, going to give us the acute angle every single time. I guess I should have mentioned that earlier. But law of sines, just based on the, eventually I'm going to have to do an inverse sine function. The inverse sine will only give us angles between 0 and 90 degrees. So if I ever do have the choice to maybe utilize law of sines, I do need to make sure if I'm solving for an angle that I'm only solving for acute angles. It would not give me any sort of obtuse angle, just as a good rule of thumb here. But this first angle that I would solve for is going to be an acute angle, no ifs, ands, or buts. I just will have to, in order to get the obtuse angle, subtract it from 180, and that actually is going to be a part of my second solution. So again, looking at this bottom sequence of triangles here, I've got two different angles I guess I should use 3 arcs for the second one. But we have 2 different angles that both are going to be named C. It's just one of them is going to be a supplement of the other, and that will be kind of the key for the rest of the problem. Once I have that angle, I should be able to figure out our A value, or our A angle in each case, and then once I have the A angle, I should be able to find the A side that corresponds with each one. So before I get too far ahead of myself, let's go ahead and just solve for this first C. Again, similar to what we did before, I'll look for which pair of things I can actually do a cross product with. So I'm going to go with 20 and sine of 29, and then that's going to get divided by 15. However, this time, instead of it just equaling a letter, now it's actually going to equal sine of a letter. So it'd be sine of C1 would equal that cross product and quotient. So 20 sine of 29 over 15. But then I would have to cancel signs, so in this case my C1 would actually equal the inverse sine, aka the arc sine of that product and quotient. So sine of 29 times a 20 all over 15, and now bring the calculator into the problem. So it would be the inverse sine of 20 sine of the angle we had, which was, again, I keep forgetting because I'm talking while I'm writing here. We've got 29 as my angle, and then divided by the side that I did know, which was 15 also. And if I press enter, notice it gives me this 40.3 or so degrees. So if I know that this C1 is 40.3 degrees, I should be able to just substitute that in place of this C1 here, and just say it's going to be whatever 180 minus 40.3 is, which if we go ahead and just for safety's sake, just subtract that on a calculator, gets me 139.7 for that second possible, sorry, 139.7, not 137.9. So 139.7. So it gives me now my key angles for each of these. So if I now know that this is 40.3 degrees in the kind of acute angled C formula, I should now be able to solve for that last A up here. So if I go ahead and just said, what would that be for A1? It would just be 180 minus the original angle 29 that I know, then minus the other angle 40.3, which then gives me a value of, for this one, if I subtract those, I've got 180 minus the 40.3 minus the 29, and that gives me a value of 110.7 degrees. So 110.7 degrees, which now should let me set up that same general ratio. I'd have sine of 29 over 15 being equal to now sine of the 110.7 over that first A side that I would solve for. So just like we did on the last couple of examples, do a cross product and divide. So for this one, it's going to be 15 times sine of 110.7, then divided by sine of 29. So 15 times sine of 110.7 divided by sine of 29. And if I press enter, it gives us that last side length for that one would be 28.9. So 28.9, which makes sense that that's the largest side because that's across from the largest angle. Now if we go with our second solution situation, just like before, I technically have 2 out of the 3 angles. So for this one, it's going to be 180 minus the original 29 that we knew, but now also minus the obtuse angle C2 of 139.7. And if I go ahead and subtract those, 180 minus 29 minus the 139.7 gives us our last angle to be a really, really tiny one, 11.3. So to solve this the rest of the way, I'm going to use that same original ratio of sine of 29 over the side B, which was 15, being equal to, this time it's just sine of the small angle 11.3 over now our little a2, or basically our last side A. And now we go through and just do the same general thing. I would just do 15 times sine of the angle, which is this 11.3 we can currently see on the screen, divided by the sine of the other angle I knew, 29, and notice this one gives me a significantly smaller side, 6.06, which that should hopefully make sense why that one's so much smaller. As well, the angle A for the second solution was actually a really, really tiny, small sliver of an angle, as you can see with my picture in the bottom left. So since that was so small, that last side A was actually going to be the smallest of all of them. 6 compared to a 15 and a 20 definitely is smaller. So again, the logic at least is following. But we had our first solution, which were the first 3 using the first angle I found. And then the second solution was a little trickier, but I could get the ball rolling with that just by taking that first angle I found, C1, subtracting it from 180, and then that now gave me 2 out of the 3 angles with my second solution to where I could find the rest of it. So I know this is likely confusing. This is the first example of that two solution situation. But again, hopefully you can kind of see like how that connection works. A lot of it just kind of goes with, if we look at this picture right here, kind of goes with the fact that there's an isosceles triangle that potentially is getting cut off. So whatever that first angle is I get, so like in this case the C1 that I get, it matches this angle that's over here. So I need to then subtract it from 180 to get the other angle that's actually inside of my second solution triangle, and that again is kind of the key to the rest of it. Again, the more you practice this, the easier it comes as far as like how you can break this down. But when it comes to a general approach, if you wanted to, you could technically go in thinking that there's always 2 solutions. And if you end up, when you do the solving for that last angle, let's say we did the 180 minus 29 minus 139.7 like we did for that second solution, if you end up subtracting that and it actually gives you an angle that's actually negative, then at that point you can kind of narrow it down and go, this must not be a 2 solution situation, it must just have a single solution, and then just finish up solving that first solution that you've identified. So again, you can always go in and just think like, I'll just assume that there's always 2 solutions, find that second C in this case. Again, it doesn't have to give us these specific letters that technically could give us a different complete named triangle, like maybe TUV. But basically we just look for which ones do I have 2 of, and then what's the other side that's been provided. You're always going to solve for whatever the different letters angle happens to be. So in this case, notice we're provided the little c or the side c, so we were kind of forced to solve for angle C first, and then that was going to be our key for our 2 solutions moving forward. All right, let's go ahead and try out a second example of this side-side angle situation. Here, notice we've kind of switched up the thing that was provided. This time I've actually been provided the 2a values instead of the 2c values or 2b values or whatever it was on the last one. I guess it was 2b values. But then I have the different letter is b this time. So if I go ahead and maybe draw a little picture for this situation, I know that my angle A is going to be that 65 degrees, which means across from it is the side A, which is where 4 would go. And then the different letter I always just throw on this kind of adjacent side because that is truly a fixed distance to be able to get there. This bottom edge, I don't know how long it could go, right? I could go as far to the right as I really needed to. But for interest of this problem, I'm going to go ahead and just kind of treat it just the same as I did before. Let's just maybe see if 4 is even big enough to close off a triangle. So I'm going in with a little more doubt than I am just saying that there has to be a solution. And if we go ahead and find that height, right, this height will always be whatever the side is that's next to the angle. So for this one, it would be that 13 length times sine of the angle provided, which is 65. If I go ahead and utilize that and go ahead and type that into the calculator, we can go ahead and see 13 sine of 65, that comes back 11.8 or so. So if that's 11.8, notice this distance 4 would not be large enough to even overcome that. So this picture actually would be accurate to a point. I probably could have made that side 4 a little bit shorter. If that side length here was 13, I probably should have made that maybe only about there. But regardless, we can go ahead and at this point say, since that's not large enough to overcome the gap, that this must be that no solution situation. Now, another way we could have approached this is just maybe instead of drawing the picture and finding the height, we could have just maybe tried setting up the ratio. So I'll just kind of show you, like, let's say we did set up the ratio of sine of 65 over 4 and then try to use that to solve for whatever that would be, side B. So it would be sine of B over 13. If we go through and just isolated the B value again, I would multiply those two across from each other, but then I also have to cancel the sign. So my capital B would end up being the inverse sine of that product, 13 with sine of 65, but then divided by this side length 4. And if I went ahead and maybe tried typing that into the calculator, oops, inverse sine first, there we go, 13 times sine of 65, close the parenthesis, then divide by 4. Notice when I try and find it, or if I even just set it up and typed it in the calculator, I feel pretty confident that I just typed everything in correctly. Notice it gives me an error domain, which basically is the calculator's way of saying, hey, there isn't actually a solution for this. So if I just do a quick double check of, is that exactly what I wanted to have typed in, which in fact it was, notice my calculator kind of also leads us in the right direction of like, oh, this must be the situation where there actually isn't a triangle that exists. Go ahead and work on a third solution. So far we've kind of seen like what would happen if I had two solutions. The last example we saw what would happen if there was no solution. So you can probably make the assumption of what this one's going to be about, but let's just maybe approach it where we're just going in thinking maybe it's going to have two solutions, maybe it's one solution, maybe it's no solution. But once again, we still have that same situation of this is an acute angle. So all I have to do is just figure out what the side lengths would be. So if I go ahead and maybe just draw that little hangman situation again, I've got the 50-degree angle is going to be my angle C. So across from it is the side C, 10. And then adjacent to it would have to be 6. And if I go ahead and maybe draw that height, if you look at it, isn't the height going to have to be less than 6? Because 6 technically is the hypotenuse of that right triangle that's being drawn right there. So if the height is less than 6 and 10 is already bigger than 6, won't that guarantee that 10 is for sure greater than the height? And in fact, the only way it could go, if I'm a little bit more accurate about this, the only way it could go is if I actually went down further to the right, because if I know that that length is 10, to go 10 the other direction, it would have to go beyond where that angle is, right? So that actually would not close off a triangle either. So this really is just a single solution or one solution situation. So at this point now I just go through and solve it the same way I would do any other law of sines problem. Set up my ratio, sine of 50 over 10, and then set it equal to the sine of whatever angle they gave us. So since that was side A, I'm going to go with angle A as that value, so this must be angle B at the top and side B at the bottom. But I would go with sine of A is what I'll need to solve for first, since they gave us side A. And just like before, do a cross product, divide, but then also cancel signs. So the angle A is going to be the inverse sine of those two things multiplied together, 6 times sine of 50, then divided by the angle, or sorry, not angle, but the side, 10. And if we go ahead and do that, we've got 6 sine of 50 divided by 10. I need to do the inverse sine first, sorry about that. So again, start over here, 6 sine 50 divided by 10, and close that off, and it gives us that this side length, or sorry, angle would be approximately 27.4 degrees. So if I go back, I know that this angle A is 27.4 degrees, which then should now give us 2 out of the 3 angles. I've got angle C was 50, I've got angle A now must be this 27.4. So I should be able to get the last angle B just by doing 180 minus the given 50 minus the 27.4 we just found. And if we go ahead and type that in, 180 minus 50 minus the 27.4, that gives us our last angle to be 102.6. So equals 102.6. So I've now got my 2 angles that I now know, so the only thing left I can do is get my last side B, and just like we did at the very beginning of the problem, we'll probably use that same ratio of sides that they provided, sine of 50 over 10, equaling in this case the sine of B, since I'm solving for side B, which we just found to be 102.6 degrees for that angle, should now let us get side B all together. I'd multiply those two first, divide by the last one there, so B is going to be equivalent to 10 sine of 102.6 divided by sine of 50, and again just pressing buttons on a calculator from here. So let's go ahead and do, if I already forgot the numbers, 10 on top. Okay, so 10 sine of 102.6 divided by the sine of the angle they gave us, 50, And if I go ahead and press enter, that gets me the 12.74-ish for that last side. Stick with the same color, 12.74. And if they gave us units like feet or centimeters, I'd make sure to use that. But with this one, it was just the two angles on that one side that I needed to find. So I've got a total of 6 things, right? The 3 I just found and the 3 that were given. So technically I've done everything I needed to solve for this triangle. All right, so maybe to just help try and solidify the how will I know if this is going to be 1, 2, or no solution at all. Again, our height is always going to be whatever the different letter is. So with this one, it looks like they've given us angle A, side A, and side B. So in this case, the different side is B. So for this one, my height's just going to be B times sine of whatever the A is, if I needed it. But ultimately, I know it's always going to be one solution, no ifs, ands, or buts, if the side across, so in this case, if the side across the angle was A, if A is greater than B, then no ifs, ands, or buts, that's going to be one solution. So let's maybe just try and identify all of those cases where that's happening. So let's look for an A that's bigger than B, and just kind of skip all of the other ones. So 6 is not greater than 13, so that's not a one solution. 25 is bigger than 20, so I would go ahead and say that yes, that's going to be one solution for this one here. Let's see, 21 bigger than 25, that's not true. 20 bigger than 8, yes, that's one solution. 12 bigger than 7, yes, that's one solution. 5 bigger than 8, no, it's not. 15 bigger than 18, no, that's not. And then 4 rad 3, is that bigger than 8? Well, rad 3 is just a little bit less than 2, so since 4 times 2 is 8, 4 times something less than 2 would have to be less than 8. So basically, those 3 that I've identified so far are the only ones that have the guaranteed one solution because the side across was larger than the other side provided. So maybe we can go ahead and identify the obtuse angles. Looks like we've got one obtuse angle right here. Across from that shape has to be the biggest side, so since the side across from that angle is not bigger, this one is for sure a no solution. Since again, it has to be the largest side across from the largest angle, so we can narrow that one down. All of the other ones, we need to go ahead and figure out what the heights are, and then from there we might be able to say whether there's no solution at all or if it actually has a single solution. So for this first one, my height is going to equal the 13 times sine of 29. So pop over and just clear out everything here. So 13 sine of 29 gives us a height of 6.3. 6 is not large enough to overcome a gap of 6.3, so since this is larger than the A value, this would be a no solution, just like the one below it. Skipping ahead to this bottom right, or second one from the bottom right. Try and find that height as well. So my height here is going to be the different lettered side, B, so 8 times sine of 54. And we're just going to see if 5 is big enough to overcome that gap, so 8 sine of 54. And that gets us 6.5 almost. So since that's approximately 6.5, again, we can look at the side that we were supposed to be 5. That's not bigger than that, so this also is a no solution. If we move on to the next couple, let's see, our height for this one is going to be the 18 times sine of 45. So 18 sine 45, that gets us 12.7-ish. 15 is large enough to overcome that gap, so since it was not the one solution, and if we just verify that it's not the no solution, that kind of tells us no matter what, this one's going to be a 2 solution. I guess I can write it in red on that white. This will be my 2. And then the last one, if we go ahead and maybe try and figure out what this one would be, our height would be 8 times sine of 60 degrees. And if we go ahead and figure out what that would be, 8 sine of 60 gives us that decimal. And we probably should figure out what 4 rad 3 as a decimal is. And if we look at it, they actually are perfectly the same. So this is that one rare case of, since the height is actually equal to the A value, that's actually one of the extra 1 solutions. Can't really fit that one on there. So this one would be 1 solution, since it actually created that specific case where the height and the A value, or the opposite side, were actually identical, which means it creates that 90-degree angle. So I actually could, if I needed to solve that one, just utilize a SOHCAHTOA or Pythagorean theorem approach, since I do have 2 out of the 3 sides. I could do that last side using Pythagorean theorem. But anyway, again, hopefully that kind of makes sense as far as like how can we narrow it down. But if all else fails, just go in assuming that there's always 2 solutions, and if you for your second solution get a negative angle somewhere, then at that point you can stop trying to do that solution, because, well, there is no such thing as a negative angle when it comes to solving these triangles. Alright, I know this video is getting long, but we got one last concept to go through. This is the area of a triangle idea. Most of us, if we've been able to make it into this class, should probably recognize that first one for area of a triangle just being 1/2 base times height. That's essentially, if I had a right triangle, I'd be able to figure out what the base and height are, and just utilize that formula to solve it. Now, if I don't have a base and a height, for example, let's say I have an oblique triangle or something that's not a right triangle, if I have the 2 sides if I have 2 sides and an angle in between them, so if that case were true, then I would end up having 3 completely different letters. Notice I have 2 lowercase letters and then 1 uppercase letter. It basically will always just turn into 1/2 the 2 small or lowercase letters multiplied together times sign of the capital letter. Because after all, what goes inside of trig is always an angle, so the capital letter only has the ability to be plugged in inside of the sine function that's being provided. So notice that pattern holds true with the second and third examples. This was just if I had some triangle ABC and gave you a side angle side situation, it would fit one of those 3 profiles, but really, if we can just kind of get this top one memorized and recognize like it's always just 1/2 times the 2 sides times sine of the only angle I knew. Good rule of thumb is how do I know whether to use that is if I have 3 different letters, 2 of which are lowercase, that means I do have 2 sides and it must be the angle in between. And then there's the last situation of what if I have all 3 sides provided. So this is one that we haven't technically solved yet. That'll be a law of cosines type problem. But let's say I just gave you a triangle and I knew the 3 sides and I just wanted to know what the area is. It looks a little bit worse than it really actually is, but it would be just the square root of s times s minus a times s minus b times s minus c, where ultimately all that s is it stands for the semi-perimeter. So if you just kind of think that word semi in most math concepts, that was hard to say, sorry about that, but like semicircle, that's really half a circle, so semi-perimeter would be half a perimeter. Hence why we just add the 3 sides together, divide by 2. That is technically what would be the formula for half a perimeter. And then ultimately, whatever that number is, I would just put that in 4 different spots, where basically I just need to get what are those 4 numbers to multiply together, and then once I get that product, I would take the square root of that result. So again, it looks way worse than it really is. And the next 2 slides will just be some examples of each, first of which will be a side angle side, and then the second will be a side side side. Alright, let's go ahead and knock out those last 2 examples here. First one here, notice we're provided with, if we look at what's there, we've got 3 different letters, 2 of which are lowercase, so that means I have 2 sides, and it must be the angle in between since it doesn't pair up with either of those 2 side variables. So in this scenario, it's just going to be the area equaling 1/2 the 2 sides multiplied together, so 10 times 15. And then times the sine of the angle provided, 53 degrees. And let's go ahead and get that typed in the calculator. 1/2 times 10 times 15 times sine of 53. Double check my numbers really quick. Yep. And press enter. It looks like we get 59.9-ish. So 59.9 square units. So we can call that just units squared, since this is now an area unit. I don't know what that was just about to be. There we go, square units. Or you can go with like SQU to represent square units as well. If we look at the second example here, notice this time I again have 3 different variables, but this time they are all lowercase. So this is more of the side 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 situation. So for that one to work, I would need to figure out what the semi-perimeter is. So from the formula, semi-perimeter, same as semicircle or same prefix, where it's just going to be whatever half the perimeter is. So it would be, I guess not a, but 6. There we go, 6 plus 8 plus 12. And then cut that in half. So 12 and 8 is 20, plus 6 more, 26. Cut in half gives me 13. So my area is going to be that semi-perimeter number used 4 different times. It's one time just 13 times the next time it's 13, take away the first side, then times 13 take away the second side, and lastly 13 minus the third side. So the last one is a 12. And if I go ahead and maybe simplify those before I actually type it in, it looks like I've just got 13 times 13 take away 6 is 7, 13 take away 8, that would be 5, and then 13 take away 12, that would be 1. So on our calculator, we've got the square root of 13 times 7 times 5 times 1. Didn't really need to do the times 1, but just to show that there's 4 numbers being multiplied inside, gives us this value of 21.3 or so. So 21.3. Again, this is an area problem, so this would be square units once again. So I'm just going to write units squared just to differentiate itself from whatever the original linear unit would have been for the actual side lengths. So I'll go ahead and box those up really quick. But anyway, hopefully this video has been helpful. Appreciate you if you had taken the time to watch at least portions of it. Hopefully you found it to be useful. But as always, if you have questions, just come find me and we'll see if we can work it out. But anyway, yeah, appreciate you taking the time watching the video. We'll catch you next time.